chaps, this is the second part. I'm not sure, I might attach it to the first lesson because the first lesson was a bit easy. But what we're going to do today, we're going to learn how to draw free body diagrams, and that's actually a really, really important skill. Okay? It sounds complicated, it's not. Okay? It really isn't. So forces, we often, okay, in physics, we represent them as an arrow. Okay? So we want to show that there's a force, we often will draw an arrow. Now the cool thing about an arrow, it gives us two bits of information. First of all, it gives us the size. So a big arrow will mean big force. Small arrow means small force. So that's the first bit of information you can get from an arrow. The second thing, it gives you a direction. Okay? So forces can be applied in different directions. So arrows are very useful for that. Now when we draw forces on an object, okay, we always have to figure out what object are we talking about. Okay, this is where normally the problem comes. Okay, if we're asked to draw a forces on an object, we need to make sure we know which object we're talking about, because there probably will be more than one object. Let's say if I'm pushing a box, okay, then what are we drawing the forces on? We're drawing the forces on me, the one who's pushing, or the box that is being pushed, or maybe the floor where the box is lying on. Okay, so there's three objects going on here. Okay, so we need to be very clear which object are we talking about. But anyway, the word free body diagram means that we're not going to draw the object. Okay? Because we don't want to start drawing a person or a box or a bird flying. So that person, that object is simply going to be a dot. Just to make it easier for us. That's what we call free body diagram. So that means there's no body. We're not going to draw the body. There is a body, but we're just not going to draw it. We're just going to draw the forces on it. Okay? So what I'm going to do, I'm going to show you maybe three, maybe four examples of free body diagrams in different objects, in different scenarios, and then I'll give you some work to do on it. Okay? So the first one is a falling pen. Okay? So the pen falls through the air. What forces are acting on it? Okay? First force, I guess you will say, is gravity, okay? Or we can call it weight. Okay? Now, obviously, the weight, gravity is always towards the center of the earth, downward, as we call it. Okay? So we're going to draw force downward. Okay? Is there any more force on it? Okay? I'm not pushing it. Okay? There's gravity. There's probably, guess, also there's air resistance. But then you've got to ask yourself, how big is it? How big is the air resistance compared to the weight? Okay? I think most of you will say yes, it's smaller. Okay? So to draw the air resistance, we're going to draw a small arrow, maybe smaller. Okay? Okay? Now I'm not going to start measuring how big you drew it. Okay? As long as it's smaller than the weight, then you'll find. Okay? Now moving next to a falling paper. Okay? A paper, I'm sure you'll guess, falls slow. It takes longer time to fall down. Why? Okay? The weight actually might be as big. In this case, it's not. But it's not that the weight necessarily is small, it's that the air resistance is bigger. Why, by the way, air resistance of a paper is bigger than the pen? When you think about it, why the air resistance that a paper feels is bigger than what a pen feels? Okay? It's to do with the surface area. Okay? If air resistance is because particles are hitting the object as it moves through them, okay? If you have a large surface area, if you spread up, okay, you experience high air resistance. I don't know if you've seen videos. A good friend of mine, he does, what do you call it? Like parachuting. Yeah, freestyle parachuting. That means they jump out of the airplane. They don't open the parachute straight away. They fall, you know, and do all kind of shapes. Okay. Now, when you want to, if you kind of spread yourself like that, lying down, you will fall a little bit slower. Okay. If you go like this, pin drop, you go faster. Okay? I'm sure you've done that when you jump belly flop onto the pool or pin drop. You know the pin drop you go through much quicker. It's painful, but it's much quicker. So, falling paper will have a certain weight or gravity, and it will also have air resistance. And the air resistance is going to be much closer or even equal to the weight than it was when we had the pen. Okay? Pen, the weight was much more than the air resistance. That was why it was falling fast and accelerating. When it comes to paper, the air resistance almost the same as the weight, if not the same. Okay? Can it be larger than the weight? Can the air resistance be larger than the weight? There are situations, yes, but when I just drop a paper, it can't. Because if the air resistance was higher, then that means it would be moving up, and that's not happening, okay? Right, last one, pushing a box. Okay, so I've got a person. I'm just going to draw that scenario here. So I've got a person pushing a box. I don't know if you can see. Yeah, you can. All right? So I want to know what's the forces on the box. In a test, okay, I need to be very clear what you want to draw the force diagrams about. So I want to draw it on the box, not on the person, on the box. Okay? So what forces are applied on the box? Let's say the box is moving to the right. So we're going to have definitely a force to the right. Okay? What are we going to call the force that the person is pushing the box? We're just going to call it a push. The push force. Okay? Now, the box, I'm just not moving the box to the air. I'm moving the box, and the box is lying on the floor, right? Okay? So there's another force acting onto the box in the opposite direction. Okay? And what do we call that? That's the force that the floor resists the motion of the box, and that's called friction. Okay? Now, the friction can be the same as the push, maybe a little bit smaller. Okay? It can be, well, it can't really be more than the push, because again, that means it will start moving downward. But it can be either the same or a little less. Okay? And there's no way for you right now to know. Okay? I need to give you extra information to know if it's the same, it's equal to the push, or less. Okay? And we will get into that later in the year. Now, are these the only two forces? No. Okay? There's another force on the box. Okay? Not by me, the person who pushed it, just by Earth. Okay? Box is pulled by gravity. I'll call it gravity now. Okay? Gravity or weight, doesn't matter. So gravity pulls the box downward. Okay? But nothing to do with me. Anything. Gravity pulls every object downward. But now, if there is gravity and the box is not moving downward, there must be another force. Okay? What do we call that force that the floor pushes the block? It's not up thrust. Okay? We call it reaction force, right? The box is pulled by gravity, so it pushes the floor downward. So that means the floor as a reaction, the force pushes the block upward. Okay? And that's called the reaction force. Okay? And actually here, I should know that the reaction force must be equal in size to the gravity. Okay? Otherwise, the box will either move up or down, depends which one is bigger. So if I know that it's just moving horizontally, straight, then these two forces are equal. These ones, I don't know if they're equal or not. Okay, guys? Right. I'll do one more thing. Let's say swimming. Okay, a swimming man. Okay? So let's say I'm swimming in this direction. Okay? Now, if I'm swimming in that direction, there must be some kind of force in this direction. And you can call it different ways. You know, you can call it push. You know, I'm pushing myself, propelling myself forward. Sometimes people call it thrust. Okay? Like an engine thrust. Okay? Push, whatever you call it, I don't mind. I'm quite easy here. Okay? Now, if there's a force that pushing me forward, okay, there must be also not must be, but there is a force that slows me down. We spoke about that. That's called water resistance. Okay? It's not air resistance, it's water resistance. And if I'm a good swimmer, I know how to minimize it by doing small shapes that will minimize the water resistance. I'm going to bump less against water particles that slow me down. Now, even if I'm in water, okay, the earth still pulls me towards its center. So there is still gravity that pulls me downward. But at the same time, I know that when I'm swimming through a pool, and even if I'm not swimming, if I'm just standing still, I don't sink, I'm floating. So if there's weight that pulls me downward, there has to be something that pushes me up. And that is the force from the water pushing me upward. We call that upthrust. Okay? So guys, even if an object moves to the side, it doesn't mean that there are no forces up and down. Okay? In fact, if you're on Earth, let's put it this way, if you're on Earth, planet Earth, or next to any other planet or star, you will feel a gravity then look up for these vertical forces. Okay? Right, I will give you underneath this a bunch of force diagrams, different scenarios, and I want you to draw the force diagram for each scenario. You need to, just as I did here, write just a dot for the object,